sound. This.
Good morning. So let's see.
Cool.
You guys see it already. That's good. And now I think I have to share my screen. You have to stop sharing there.
Yes. Yeah,
that looks good.
Maybe can I ask you? It's the last session, so normally there's a good trick. What I do when I go to a conference is I always need to think that I have at least one question. It makes me stay awake during conferences, actually. So it's just a good trick, and try to have one. I think it can be interesting for the last one that we have a little bit of debate about also different lectures maybe that you have seen now about the transforming timber. And it went from very detailed and people that are working on the timber itself with a factory and what challenges they see ahead, to the very intellectual approach on timber, and even the ones from carpenters, how they see the evolution of timber at the moment. So I think there's quite a lot of aspects, and I think you will also see it back in some of the reflections that Oliver can bring us today.
Thank you. And yeah, thank you, Klaus, for having me. It's a pleasure to be here today and meet you, and yeah, maybe even discuss with you from the lineup of the speakers. I have to say, you must have had a great week or two of lectures and input. And I'm not especially an expert on timber structures, but at the digital design unit, the unit that I'm heading in the Department of Architecture at TU Darmstadt, we are interested in computational design, in digital fabrication, and in robotics. And we always try to see the whole process as one thing, as one continuous chain that is not linear, but where the way we build and the way materialize ideally already informs the way we design and ideate, how we come up with new design ideas. I would like to talk about three topics and three research trajectories of the DDU that deal with the question of how can we build better in the future, how can we build differently, and how we can use digital tools in design and fabrication to make that happen. And well, I have to rush through it in 45 minutes. So maybe we can actually very quickly go through this slide. I'm sure almost every lecture was talking about these aspects. Have you seen the diagrams in previous lectures? The productivity of the construction industry, the demand for new construction in the future? No? Yeah, I'm sure you saw that, right? We are low in productivity. We need to build a hell lot of new buildings for a rising global population. Currently, what we do is we increase material consumption and we produce a lot of waste. And if we keep on doing that in the way we do it right now, to fulfill the demand of construction that we will have in the coming 40 years, we will probably kill this planet. So our discipline, the architecture and the construction industry, are key in how the future will unfold. And more this also becomes obvious in mainstream media. People are discussing that, and you have been working with timber in the past 2 weeks intensively, and it makes a lot of sense if you read that headline from The Guardian from 2019 already. I would like today to talk about the use of concrete as well, but how we can maybe find different ways of using concrete, of reusing concrete, and how a modular design and fabrication strategy can help to keep material and building components in the loop. The problem that we are facing, one of them is that buildings like this one become obsolete because of their function. They're not useful anymore. They don't comply to security standards for escape routes, or they don't comply to energy consumption standards. So what happens is that, well, they are torn down, or like this building very spectacularly being blasted away in actually the city center of Frankfurt, next to a very important museum. So it was, well, an impressive piece of engineering, of course, to make that building fold and yeah, almost disappear in this cloud of dust, not destroying the rest of the city. But if we think about it, it's really crazy. And if I show you the next slide, it's even more crazy. This is on the left-hand side, the building, how it was built in 1972. We just saw the demolition. And then in 2018, there was a new high-rise being built at the same spot. You see that little tower with the cupola on top. It's the exact same perspective here. On the right-hand side, it's the Senckenberg Museum. And you wonder, is it really necessary to blast the building away, to maybe downcycle the concrete that was used there for road construction? Or are there any other more smarter ways to use the material and reuse the material and keep the building elements in the loop? Because structurally, that building was actually perfect. Yeah. So one thing that we thought about was a digital process chain in which we thought it would be good, instead of blasting buildings away, to actually deconstruct them, which would require somehow 3D scanning them. Here you see a drone flies above the structure, scanning the entire structure. And then there are two processes. One is a digital process and one is the real, or well, better, the physical process, in which first through this 3D scanning, you receive point clouds, and the point clouds can be transferred into geometrical elements and further developed into BIM elements. So it's a building catalog that you can design with, and then you have the real elements that are cut out of the building and that are refurbished to be used for future buildings. So in that sense, what we suggested here is to, in the first run, do some urban mining. You mine the material, but then you would refurbish the single building elements so that they can, in the future, be used as dry joint constructions that are easily to assemble, but also to disassemble, and maybe to be reassembled in future structures again and again. What we do at university is we write grants to get money to do research. We proposed this idea, and while waiting for a committee to decide whether we get that grant or not, we were exploring this idea with the students at the TU Darmstadt, and there was Jiangpeng Chen, who did his master thesis on this topic, saying, well, what if we take out building elements, and he proposed to urban mine them and build new structures, in this case, a bridge. So there's, on the left-hand side, there's a bridge design. On the right-hand side, there's a material stock, and then he would see which of the building elements he could use to realize that bridge. But he also said, well, we can do more. We cannot maybe only do a bridge, but we could also design a roof or a tower with these existing elements. And well, since you never really know the amount of steel reinforcement that is in such an existing concrete element, you rather design a structure which is only exposed to compression, because as you know, concrete can take a lot of compression, and it's not so good in taking tension forces. That's why the steel is in the concrete. But if you don't know about the amount and the quality of steel, you rather design compression-only structures. Furthermore, you need to recombine these linear elements that has previously been used as columns. And so he came up with a geometric system to develop a node logic. In this case, he 3D printed a connecting piece, and then he jumped from his design part to the fabrication part, and he used our small robots, and he brought this table saw into our lab, which was terribly loud, but he kind of invented the entire process with the material feeding system, bringing him the elements, and then the robot, as you have just seen here, takes the element and cuts it in a kind of a weird angle. That's what the robot is good for. It can place an element in a very precise geometric orientation to make these cuts. Then you get a lot of linear elements, and then he 3D printed these black nodes, and finally spent one day and I think also one night to dry join this bridge together. So nothing is glued here. It's only dry joined linear elements and these nodal constructions. With other students, we tried to think a little bit larger about the topic, and maybe also in a more poetic way. Katarina Koska made a design proposal where she said, well, if we tear down buildings, we have to ideally immediately take the elements and build a new one. But maybe there's a gap, a time gap in between, so material needs to be stored somewhere. So her proposal was for an EBA competition in Basel to say, let's combine material storage with bus stops in the city. So she invents this bus which comes with this extra car on the back. So it's not only people traveling with the bus, but also the concrete elements that travel with the bus. And sometimes they are picked and taken to a construction site. Sometimes they are delivered to a bus stop that is growing and shrinking over time. She also said it's a little bit like in a hospital. If you urban mine these elements, you need to check what's the status. Yeah. So sometimes they have a few cracks and they need some kind of little bit of plastic surgery to let them look good again. Sometimes you have to amputate because it won't work any longer. And sometimes maybe these columns even die and are then recycled or downcycled for road constructions. But the idea is to have the element in the loop as long as possible, and to make storage also a piece of architecture intervention as well. Another group was looking in how to make subtle cuts in these columns to let them pile in a different way and to come up with structures that are maybe not so usual as a bus stop to find, but that react on the idea of dry jointing elements together and take them apart if they are needed elsewhere. So while we did that, the reviewers looked at our research proposal, and finally we were lucky and could start also a research project that looks at this aspect. It's called Fantastile 2.0. It's precast concrete component 2.0. The idea of taking something that is there and make it a precast concrete component again. So again, we looked at this workflow, and that workflow includes, first of all, 3D scanning. This is the architecture school in Darmstadt. We have a great lobby with the espresso bar on the entrance floor. So you're all invited to come by and visit us, or maybe have an Erasmus exchange. And what you see here is the point cloud version of the architecture school that was actually scanned by a stationary laser scanner. But once you have the point cloud, you load it into Rhino, and you can make these fly-throughs. And we speculated about identifying beams and identifying columns that could be harvested for future buildings in case we would tear down our architecture school. In the research project, we use different tools. We collaborate with a scanning company called Faro that use these hand scanners to produce these kind of point clouds that look like this. So millions of points. Every point comes with a color value, with RGB value. So you have this kind of fascinating effect of seeing something in 3D, but almost, if you go a little bit further away, like a photography that dissolves once you come closer. That needs to be then reinterpreted and step by step, and ideally automatically be transformed into geometric elements again. And then our engineering partners plan how and where to cut building elements from a building that is supposed to be torn down. And these yellow marked columns and beams are meant to become the basis for a lot of maybe a lot of different structures in the future. So how do you then join these elements? Ideally, you join them in a way that they are easily deconstructible again. And so we do a lot of research on interlocking structures, on dry joint structures, also concrete dry joint structures that can be disassembled and reassembled. We explore how 3D scanning existing objects like the stones and 3D printing together can be used to combine the existing with the new one, like this orange 3D printed plastic blocks that become the perfect connectors or adapters for the structures. And we use computational tools to explore the combinatorial potential of elements. So you see here 40 elements that are combined and recombined in many different ways. So computational power is used not to make every building element unique and that it fits only in one particular position in a construction, but we rather use computation to explore how these parts can be differently combined. And on the right-hand side, our partner Harald Kloft at TU Braunschweig and his team are looking at reversible and dry joint constructions. What do you harvest? Well, it's not so easy. We found out to find somebody that gives you concrete pieces. We found that at the campus of TU Darmstadt, supposed to be torn down. And usually these things, as I showed in the video, are destroyed and crushed down for gravel, for road construction. So we said, no, we would like to saw them, to saw these elements, to reuse them. And we were allowed to do that. This is how it looked in between the funny leftovers of a former bridge. And then the sawing guys come with really serious blades, and the saw with 40 horsepower. And you might have seen in the video, I'll run it again, that the column is jumping. Yeah? So we cut it on the ground, and at the same time we pulled on the top, and it was kind of flying away. So this is the stuff we now design with, and this stuff got transported into the digital fabrication laboratory at the TU Braunschweig, where they have these sawing blades connected to robots to very precisely cut the elements. And the elements are cut in a way that they allow for dry joining them together. If you do that, it makes a lot of sense to also assess the amount of energy you spend into it. Does it all make sense? Or do you invest maybe even more energy than building new? So this is something that we explore in parallel. There's a life cycle analysis going on and looks at the different ways of keeping building elements in the loop. The project is facilitated by the DDU in collaboration with the ITE, Harald Kloft, and the Unit for Sustainable Design in Darmstadt, as well as Faro, the 3D scanning company that is interested in transferring these ideas into the market. Let's assume we don't urban mine the elements, but we design new components. How can we design the components in a way that they can be used for assembly, disassembly, reassembly? And what does it take to assemble those elements together? That's something we look at in another research project called Tactile Robotic Assembly. And it is about how we can use robots to ideally autonomously assemble elements and disassemble them and reassemble them. One important starting point is the module, and this is one we didn't invent ourselves, but it was invented by a researcher called Sheguan Chi in Taiwan, and it is called an SL block. It's a module that is made from 8 voxels. 4 of them form an S, 4 of them form an L, and together you get this thing, this weird thing, which is called an SL block. And you can combine 2 of those SL blocks, which is called an engagement. And what's interesting is that these elements can be combined in many different ways. So you can create linear interlocking structures that allow you to span. So maybe that could become a beam. You have other forms of combinations where you rather create closed blocks, like these cubes. There are cantilevering structures. There are spiraling structures. I'll rush through them. But yeah, the message is you have very repetitive and very simple module that can be assembled in very different ways. And you can then also combine these different engagements and make larger configurations that create all sorts of sometimes weird, but sometimes also very basic forms. So taking that as a starting point, you could think of building elements like columns or walls or floor slabs in a completely different way. Usually we see them as one continuously cast element or a timber element. In this case, we see building elements made out of thousands of those modules, always dry joined together, which means that they can be disassembled and they can be reassembled in completely different shapes that I'm rushing through now. One thing that is interesting about it is that you could start with this SL block as the basic unit, and you can go through all these different levels of the engagements of the SL strands, and you finally come to a higher level assembly, which creates then building components like beams or columns that could possibly be integrated into much more conventional structures than the ones that I've just shown, like these ones. So you can create this kind of sculptural elements, but you can also create very simple beam-like structures that could be used in existing structures. So the element is repetitive, it's not changing, but what can be changed is the material. So we produce quite a lot of these SL blocks from various materials. We looked, of course, at concrete, but also at wooden structures. We 3D printed them. We used acrylic to have translucent or transparent elements. And well, the common denominator is that they can be assembled into coherent structures while changing the material. Here it is a bit of a random configuration, which I think looks beautiful. It's not responding, for example, to structural needs, but you could think of structures where, well, in zones of compression, you would use concrete elements. In large spanning areas, you would rather have lightweight wooden elements, and maybe you have ones that regulate humidity or direct the natural light in different ways. Eugene Liu explored that as his master thesis, and he built this kind of demonstrator in our building, and is now continuing the same topic within the research project Tactile Robotic Assembly. So if you have these small elements, it's quite a lot of work to put them together. So you want to automatize that. And our conceptual idea, again, is, of course, to say, well, they are assembled somewhere. They might be disassembled and reassembled into other kinds of parts. Maybe we create larger beams out of that and then have larger robots like these orange ones that then put these larger parts together into structures like bridges. One project where we looked at assembly and disassembly was an installation for a light festival in Frankfurt, where the robot was part of a kind of installation sculpture made from these foam blocks, and the robot sits in the center and is constantly rearranging this setup. And you can see there are these words that are projected like an anamorphic projection onto the onto this installation, and the word is changing its meaning when the light is changing its colors. You can see act and react, but you also have this robot that is constantly rearranging the modules and puts them in different places. You can also see that these blocks are super lightweight. They are designed in a way that they fall in place. They kind of self-calibrate when they are positioned. So that was all done by a blind robot, pre-programmed by us. That was only going through a pre-programmed sequence of assembly and disassembly. If you look at the SL blocks, then you see that the assembly is a little bit more tricky here. There's quite a bit of friction involved, so it requires tactile sensitivity to combine them together. And that's that was the moment where we teamed up with roboticists from the TU Darmstadt that are exploring tactile sensing. And you can see some of their experiments here. There's this robot hand that has fingers with a tactile sensor that knows whether it has a heavy element, which is hard, or whether it's grabbing a soft element and it should not destroy the element when grabbing it. In our project, we used a different system. You see the gripper here, and tactility is combined with image processing. So you have a gripper that grabs something, and it's equipped on both sides with a gel pad, which can deform and has these black dots. And when it grabs something, this pad deforms, and this deformation is then recorded by a small camera that sits behind it. And you can see that here. So different forces create different deformations of this dotted pattern. And this system uses then reinforcement learning to interpret the images and the deformation of this pattern to develop an understanding of what it is actually seeing. Yeah? So through the deformation of this gel pad, the system is able to reconstruct the surface structure of the object that is grabbing, or it also develops an understanding whether something that it grabs is maybe slipping or moving. Yeah? So this was the starting point where we said, well, if the robot knows what it grabs, that's cool, because then we don't need to sort the concrete blocks from the wooden blocks, from the foam blocks, just taking one and checking how heavy it is and knows whether it's the one it needs to have or whether it needs to grab a different one. This is a different gripper, but same technology. And you see here that image on the screen that is the result of the movement of this block that is just grabbed. So this allows us to tell the robot what's going on while assembling. If you move elements around, it's also good to know where they are. So you need a tracking system. What we used here are two things. One are these April tags that are glued onto the elements, and then you see these gray dots, which are reflective dots for a camera system for motion tracking, and that allows us to digitally record how elements are moved through space. Now, the group that we are working with, it's the IAS group, Intelligent Autonomous Systems. They use robots very differently from the way they are used in architecture. And they teach them. And it's an extremely interesting process. You can see here, if they want a robot to play table tennis, then what they do is they kind of make all joints weak and open, and then the human guides the robot how to play table tennis, and the robot is recording the principal movements, the joint accelerations. So it has a kind of rough idea of what table tennis means. And then it's playing, and there's a camera system that tracks the ball. And whenever the ball hits the table, the robot gets a reward. Whenever the ball does not hit the table or goes into the net, it gets punished. And through this reinforcement learning process, the robot suddenly is able to play table tennis without understanding what table tennis is. It's just the reinforcement learning and the rewarding that helps him to do that. And we thought that is a great approach that we could also maybe use for assembling modules. And here you see We assembled elements by hand. We recorded that to tell the robot how this movement is generally happening. We also did it by remote controlling the robot. You see the guy is using the arrows on the keyboard to kind of remote control the robot, so that the robot then has a general understanding of what it means to bring these elements together. And then next step is we let him do it on his own. So the robot is assembling. Whenever there's a collision between two parts, and maybe whenever there's too much friction between the elements, then you can imagine this jail pad in the gripper is deforming. And if it deforms too much, then the robot is stopping and tries to approach the assembly procedure from a different angle. And again, we have a rewarding system that rewards for kind of smooth assembly and that punishes for too much collisions or too much friction in the system. So it's the human demonstration that is then followed by an artificial reinforcement learning process. What we are currently looking at is, on one hand, to use the tactile sensors, and on the other hand, with a new generation of robots, like you can see them on the right-hand side, where every joint is equipped with torque sensors that also can measure whether there are any high forces during the assembly process. We try to combine the tactile information with the other sensors to improve the process. Yeah, you need a lot of cameras, of course, to look at the element from every angle. While this is the job of the computer scientists and the robotists, we do the same in parallel in our architectural robotic lab. But what we do is we slightly redesign the SL blocks so that they are a little bit easier to assemble. You see these rounded off edges that help to maybe self-calibrate, that reduce the friction during the assembly. And to test that, we use our blind robots, not equipped with any sensors, to put these elements together. So the idea in the project is to really approach it from two sides. One is the robotic sensory process, and one is to design elements from an architecture perspective that are made to be assembled with the robot and not by humans. And let's say if we manage to do that, maybe this is the element size 1-to-1. Yeah? We are not interested currently in scaling up the building block, but we say, well, maybe we build a column that is made out of thousands of these elements, but we have autonomous robots that work 24/7 and assemble and disassemble these elements, and the time they need is not the decisive factor there. Not any longer the decisive factor. There are challenges ahead. You can see tolerances add up, and tolerances are not really welcome in such a system that relies on friction. We are currently also looking at post-tensioning the elements, so having cables that run through them to make them more stable. But we also think of how we can translate an architecture construction that is made from all these different layers into one that exclusively works with one geometric system, but that is differentiated in its materials. So you have insulating SL blocks, you have load-bearing SL blocks, you have ones that might even become the frame of the window. And yeah, of course, we could imagine that elements that exist in our architecture department are no longer continuous, but are maybe made from these blocks that, if they are not used anymore in the future, become something new, like the bridge, for example. This is a project that requires not only architects, but also our friends from the robotics and computer science department. And it's actually a very inspiring interdisciplinary collaboration that we are currently working with. Last project I briefly would like to show is a studio that we are currently running, and it's called Animate Concrete. And it tries to explore a little bit the idea, well, imagine we have this world where everything can be assembled and disassembled and reassembled. What could that mean design-wise? And also, what should that mean for concrete elements if they are meant to be moved around? How do we as humans interact with them? And can we think of different kinds of spaces in construction there? And we started in April with this image. It's from an exhibition called Flying Panels. And this exhibition and research project explored how in the 1960s, the flying panel, which at the end hangs on a crane, but the crane is not shown, it's just flying there, how that was the promise of the future. And not only in Eastern Europe and Soviet Union, but that was also something that became very popular in the rest of Europe. For example, in Sweden, there was a million program where in 1 decade, 1 million apartments have been built with precast concrete components. And well, we should all not fly so much because, you know, CO2 emissions, and we think also concrete elements should not fly, but they should rather walk. And so this was the starting point for us to explore whether we could have elements that move. And the way we do it, I'll show that in a minute. This is again Darmstadt Architecture School, brutalist building, shots from the late 1960s, shortly after finishing construction works. It looks pretty much similar today, a little bit older and a bit of graffiti here and there. It's interesting because in 2019, this building was built and it was celebrated for low-cost housing. And what the architects propose here is to use prefabricated industrial building components to build cheap, not for industrial facilities, but for housing. What I think is interesting is that 2019, 1968, there's almost no innovation in concrete in 60 years. So we should really, as a discipline, think whether that's really the way to go into the future. Yeah? And if you look at the flying panels, well, what has been a positive vision is just the everyday construction site. So we were wondering, what if panels not fly, but if they walk and maybe they roll around, they are again dry joint. So can be assembled, can be disassembled. And this is what we are currently looking at with our students. And one technology that we developed that is in use here is the rotoforming of concrete. You know, where if you get these chocolate Easter bunnies, they are hollow. And the way it is done is you have an Easter bunny form made out of 2 parts. You put a little bit of liquid hot chocolate in, you close the form, and then you rotate so that the liquid chocolate is spreading all over the surface of the form. We try to do the same with concrete. You can see that here. And what's interesting about the process is that you, of course, use a lot less material because the elements are not solid, and having less concrete means in the casting process that you have less hydrostatic pressure on the formwork, which means that you can have super lightweight formwork as well. So the idea would be to save material for the formwork itself as for the concrete element in itself. Here, this is concrete. This is a latex balloon, a large one that you use for birthday parties. That is pre-stressed in different directions, and that served as the formwork for this concrete element that you can see here is produced in various layers. So it's a kind of additive procedure where layer by layer is filled into this node. And we consider that to be maybe the node of a spatial space frame structure. Again, with students, we explore what's possible with this kind of fabrication technique of rotoforming. Students were simulating this pre-stressing of the membranes, and then we're casting, and you can see sometimes it works out, sometimes elements break. That's research, that's experimenting, but you can also see how the digital prediction of the behavior of pre-stressed membranes kind of fits to what really happens then in physical reality. So there was a group looking at columns, there was a group looking at panels, ceiling panels, of floor panels, beams, modules, and so this is how we did it. We kind of invented our own machines and we're crawling underneath them to fabricate different kinds of elements that then ended in an exhibition where you can see on the panels in the back, there was a little bit of process documentation. There was also a speculation of what could that be as a building element. See a lot of happy students after intensive workshop time, but also a kind of map that was reflecting on the different building elements that were produced there and what they could become in the future. Was quite a bit of manual work. See, like it's a little bit like in the bakery, rotoforming by hand, but in the next step, we scaled up the process, got a bigger robot, and teamed up with an industry partner to produce hollow column segments, again with the membrane formwork, twisted elements that you would otherwise produce by probably milling the formwork out of foam to generate this kind of complex shape. Whenever we produce something, we 3D scan that and we compare it with the digital model to see how much the physical form deviates from the one we planned, and that led to a prototype of this twisted column that is hollow, and that could then in the next step, in this case, just be working as a permanent formwork for a more conventional column. So there's no reinforcement involved here. It's just the outer surface for a load-bearing column to come. What becomes very clear is that this entire thing is a material system that requires knowledge of the material behavior of the formwork membranes as well as the concrete. You have to develop the machines or develop the robotic trajectories to do that. And of course, you have to have a digital design process to make all that happen. And all these three steps cannot be separated from each other, but they are part of one coherent system and workflow. Students then speculated what it could mean for architecture if this would be available in one-to-one. That was in 2019, and now we are interested in these mobile elements currently. So elements that could rotate, that could reorient, and therefore afford different kinds of uses for people to interact with. Furthermore, as I said, the idea of joining them together and make them a construction is something we are interested in, but also how people interact with, well, what might be a construction element. It was not in this case not designed to be one, but what you see here is there is something made possible because of the center of mass being in a very low location here. Yeah? Now imagine if you have a hollow element that comes out of the rotoforming process. After you have the hollow shape, you can still fill in some concrete here and there. And with that, you can control the location of the center of mass of something that looks massive, is actually hollow, and behaves in a kind of weird way, maybe like this thing. So this is what we're currently working with. You can see here the rotoforming process, the liquid that is spread all over the surface, that then leads to elements that are massive here and here, but they are hollow here. So if you see them from the other side and you consider them as being massive, you would be surprised by their behavior, because the center of mass is in a location you don't expect it to be. So this is something that students designing the behavior of an object by placing the center of mass in weird locations. We are also interested in interlocking these structures, dry joining them. So what is the logic behind them so that they fit together in different ways, and also that they might be walking and rolling around to form different kinds of assemblies. And if that's possible, then you can come up with various aggregations, how they could form a structure. And what's interesting is that suddenly this moment of rolling things into each other requires certain geometric features that allows that prevent two elements that meet to collide, or to not be able to put together because this fillet side of the yellow block needs to be there for the gray one to slide in. So these are parametric investigations that our students are currently doing. And then that leads to this kind of weird objects that come together in certain movements and then roll out again and reconfigure with other elements digitally, but then also physically. It's always important to combine the digital work, of course, with the physical manifestations. And you can see it's always a little bit more tricky in the physical reality than in the digital one. So this group is currently busy with the robot doing serial production of the elements with this big frame rotating around with the aim to create walking, dry joint, reconfigurable elements that allow people also to interact with, and that allow building elements maybe to exceed the lifespan of a single building, but travel through time and space. And this is where we are right now. Thank you very much for your attention.
see everybody has a question now. So, maybe there's one of you at least that has a question. See, over there.
Thank you for coming. I'd like to know, is it possible to cut your shapes that you use in existing buildings and then try to as a research partner?
You mean these kind of shapes? Well, if you look at current, it's an interesting question. If you look at current technologies, you see these massive saw blades with 40 horsepower saws, which are then bolted to the building that you want to cut on a kind of linear axis, and then it moves and it cuts. And it's quite a scary process because it needs to cut through the concrete, through the reinforcement, and it does that in a linear fashion. So to have a kind of fillet shape or something like that, with like you would consider that a cut like you do it with a hot wire cutting device, right? This is something that you can do in steel. But so far, I would say not in concrete. No.
There was another question there. Yeah. Oui, oui, oui. Allez-y, je le traduirai.
Concernant le réemploi du béton qu'on a vu au début, et peut-être du béton récupéré, certaines sciées, réguler, est-ce qu'avec les moyens mis en œuvre, des énormes scies nécessaires en fait, pour aboutir à récupérer du béton, est-ce que c'est voulu à se démocratiser ça? Est-ce que c'est rentable? Ou est-ce qu'on se rend compte à la longue que c'est tellement plus que de béton, que le côté business prend un peu le dessus, en fait, ça.
So the question is, indeed, if you look at all the means that you have to put in place to cut down and recycle that building, is it really something that we can envisage for the future? I think you already gave somehow the answer before, but I think it's a very good question.
Yeah, it's a super important question, and it's one of the reasons why we do the project, because I'm convinced that you have to try it. You have to do the life cycle assessment. You have to, what we look at is the energy consumption of every tool that we use to cut. So that at the end of the day, you have a proper understanding of what it means. We don't have that yet, and we want to gain it. And then it depends on many factors. Yeah. So currently, we harvested these elements in Darmstadt, and then a truck came from Braunschweig, 300 kilometers, to bring it to the cutting lab. That's stupid. You should not do that. Yeah. Ideally, that needs to happen with very little transport in between, of course. You also don't want to store it because you have to bring it somewhere. You have to get it from the truck and on the truck. Besides the technologies of cutting, you need to have a logistic system. You need to have a marketplace also where demand and need is meeting, so that ideally I can say, well, I'm planning to build something in 2 years. Who in my area is planning to tear something down, and does that fit? And for that, it could be super interesting to 3D scan something that is still there, might be taken down in 2, 3, 5 years, so that the building owner can also decide, well, is that a building that I rent out? Or is that actually a material storage for somebody else to become a building? Yeah? And it also needs probably a different kind of taxation. Yeah? Transport is too cheap. Building with concrete is too cheap. And if you would consider CO2 emissions that happen when you build with concrete, And if you would convert them into taxation, and that is on the way on EU level, then suddenly it becomes economically also interesting. Currently, it economically doesn't make sense. On the other hand, what we see in Frankfurt is that we run out of sand for the concrete for all the high-rise buildings that are being currently built. We know that there's sand below the city forest, but imagine, the societal impact of getting rid of the forest to get the sand underneath. It's impossible. So what happens is that sand comes from other parts of the planet to Germany to make concrete. If this is still cheaper than reusing elements, then we need to have different kinds of regulations. So it's a super complex problem and challenge, and sometimes I feel like what we are doing is the simplest part to develop this technical workflow. It's the political, the economic model around it that needs to change, and that will take a while.
On the other hand, maybe just to answer, it's specifically the position of universities and of you students that should be asking these questions. I think this is where what I really liked in your presentation is a lot of the thinking that goes behind it goes together also with the students and what they develop in master years. Like you guys, you have your memoir and your PFE to do. And these are typically questions that are asked in that round. So it's within those master years that the critical thinking of students is already happening and can actually have a total added value. And then another remark that I would have is, and often, sorry, these things, of course, at first, they are not economical, because that's not what the university is doing. They need to check what is the possibilities and ask critical questions to the society. So I think that's a very important one here. And of course, you're checking it with the life cycle. And also indeed, in France, it's already like that. If you demolish a building, all the building components need to be stored in specific ways and need to be treated in specific ways. Actually, the one where you do have to cut up the building with this saw, you have to do it already. You cannot go on site and just, in France, it's not possible anymore to blow up a building because there's too many building components. So the regulation already demands that you break it up. So the saw is there. If you went around in Paris, sometimes on construction sites, you see that big saw, the one that they use, and it's super dangerous, to be honest. I mean, you shouldn't be so close, like the guy there on the video, because it cuts through everything, huh? So you're really dead after that. But if you think that we have to store everything already that is coming from construction site, and it's true at the moment with dry components, it's sort of easier. Like I think Clément can talk to you about it because they are doing it for timber. So the dry components for timber are coming out of the building and are scanned automatically already. So they have a storage space in Saint-Denis where you can actually go and find on the internet again with all the measurements that you need if you can reuse it. And look at what Rotor is doing since 10 years. It's the same thing, right? And now it's getting to building components. And indeed, if the economy of things becomes more important, imagine what that will do with the BIM modeling also. All of a sudden, people would like to know what is really built in their building, so you can reuse it later. So each of the components in a building could become an asset also to be sold later. So you have a marketplace for this kind of products, I think. But this is all questions that are happening at university level, and unfortunately, indeed, not enough on political level, I think. So that's probably a question there. Sorry, there was.
Two things. First thing to interrupt this discussion right now. This marketplace that you're talking about is actually being developed at the University of Animate at TU Vienna. I don't know if you know about this kind of development. I've been to a couple lectures with those guys. So,
yeah, they have it in Switzerland too, actually already. So there's, and they put these tags on it also on building components so that you can read all the information. So when you build, you put the tag with all the information, the volumes, whatever, that you can reuse it indeed.
There are quite a few initiatives, which is great, I think, because I think we need to attack it from different angles and see which one is the best. There's one in Vienna, there's Rotor, there's Concula in Germany, and ideally they have a little bit of competition, but they also share the experience that they want to progress. Yeah.
But the other thing, do you have what is your approach to doing a structural analysis when you cut a column or a beam? I think it's an issue that you don't really know what is inside, how much what is the steel grade and so on.
Yeah. The structural capacity of an existing element, that's the question. Well, there are different ways to do that. You might find some old plans, documentation of what has been built. In the future, there might be something which is called a material passport, right? The tag that tells you the amount of reinforcement that is in there. There are tools that allow you through magnetic fields to check the reinforcement from the outside. You might, currently if you need funding, you better write artificial intelligence in your grant application. So I could imagine you cut a column and you look at the cut of the reinforcement and looking at many of them, the system learns what kind of reinforcement that could be. And I think that is interesting in our context. If we don't know, well, then let's design compression-only constructions. Then we don't need to worry any longer about the reinforcement because we know the concrete can take the compression. So that it might mean that we drill a hole all the way through the element, and then we get a cable through it and we post-tension it. Yeah, exactly. Yeah. Or you build certain geometries that only create compression forces. And I think the design approach is something we should also not forget, because it's a very technical topic, but it also is a question of how you solve these problems architecturally. And it's the same with well, if we in the future are not allowed to build everything new, then we also need to change the way we design. Not start with a blank piece of paper and draw something, but first look at what's there. It's like, you come home, you open the fridge and you cook with what's there. So is this our new design approach? It is different from what we do now. And what I hear from people like Concula, who do this trading of elements, but also consult architectural offices, is that's a challenge because it requires a different way of designing. And that's also, if we think of universities, that is something that maybe we could think about and take out into practice, because it will definitely come.
Yeah, and maybe just to come back on the previous discussion too there, if you look at all the buildings from Rome, they have all been redone with stones from previous buildings, for example. All of them. Like since centuries, we have been reusing materials. Only the last 100 years, because concrete was a new material also. So in a way, at least reinforced concrete, we didn't really do it. And we were all in the roaring 20s already, happy to use a new material. And then we're again in the 20s, it's 100 years later. And if you see what we have been doing the last 100 years, it was everybody was very happy. It brought a lot of possibilities, but I think we're back to think, what can we reuse? Can we demolish and reuse the things? And I think it's a perfect timing. But you have a question, yeah. No? Because just one thing, I think it's interesting in your lecture also, you don't oppose directly the digital against the analog also, because in France we have a resurgence of craftsmanship. People are looking at it, what can we learn from it? There's also natural materials. And instead of that, you also say, yes, okay, that's true, but we have a lot of concrete. What will we do with it? And I think here for you guys, you're at the end of your bachelor's. So there's an important lesson. Do we still design the same way we should be designing? What is the use of digital things? Is AI something that architects will be using? Look at the interdisciplinarity that you showed here. We don't have it at French universities. We are not in a campus here. We just try to build a double degree now. So it's the first time we do it here. And I think this discussions between different sciences also needs to come back much more to the architectural field, because you guys at least have an aesthetical, an ethical, a sociological, and all the other aspects that we still need for this too. Not only the material science and this digital designs. And I think there you ask a lot of questions in your approach also with the students. I think this is an important lesson for our students. It's not reinforced learning we're trying to do. So that for me alone from the lecture is super important for you guys to take with you also. Don't oppose digital to analog, don't oppose craftsmanship to what the digital is doing. We will need everything from that, I think. So, sorry, you had a question.
Yeah, it's about the scale of the project that we are doing now. For example, your ideas can be done in I think about it's my own personal thoughts about it. Like you can build all this principle of succession. Like you add a port and a port on a port to make a big one and a big column and a big wall and all these kind of things. But the thing that at the end, all the regulations that you have to face on to prove that all this structure is can be built in, all the steps that you have to prove it. For example, if you want to try a way of building that is not accepted, for example, all the all this kind of,
for the load-bearing structures,
all the structure, all
load
this, you have to
transfer.
prove everything. And I think that all these kind of disruptive ways that exterior elements that disrupt the architectural way of building, it's very negative. For example, if you want to try a new way of doing things and you are the specialist in engineering and you know better, you know better than someone that works at I don't know at an office on an administrative office for all the government. And how do you think all these external elements are disrupting the? For example, you talked about the way that all the precast walls in the Soviet era they invented this kind of ways, but now you didn't develop any new ways because there's a lot of restrictions that are just put in front of us. Well, over administrative, over regulation, over everything. And how do you think that it affects the today's architecture development or what just told you? What do you think about that?
Yeah, I mean, coming from Germany, I can confirm that there's almost an over-regulation of our sector and how buildings are being built, which then also means that building new buildings is quite expensive. And we have a lack of 400,000 apartments in Germany, and things are super slow because of that. In my role, I rather say, well, ideally, rules change because of technical innovations. If I accept the rules, then I would be stuck and nothing would change. Let's say I'm in the luxury position at academia to come up with new ideas. The TU Darmstadt, and I think a lot of German universities are currently pushing what they call the transfer. How do you get out of academia into practice? So whenever you team up with industry partners, university loves that. They can tell the story. Hey, tax money is used to do something which makes sense. And I see that in a positive way because it allows us to discuss with industry partner questions that really come from practice. And at the same time, we do things that they would never do because in their everyday life, they cannot say, I don't care about regulations. This is what we can do. they do something else, and kind of meet in the middle and be in a constant dialogue is something that helps. And then it is in fact kind of frustrating if you see how something like ultra high performance concrete that can do quite a lot is used in Switzerland in a completely different way compared to Germany, because they are maybe a little bit more daring or experimental. Well, this is to a certain extent the system in which we act, and we use the academic freedom to maybe challenge that here and there, ignore certain regulations to test something new. But it's a long way to go.
This is what we all want, and that's why me, for example, I'm working in the academics and in the private sector, because I want to push on both levels, of course. And it's true, you have to push it all the time. But that's our moral obligation, I think. We have no choice. And so universities are an ideal platform also to test all these things. And this is where the role of an architecture university also to have a reflection on materials, how they are used, and not only just aesthetical values. I think that's really important. So that's also why we created the Fab Lab here in Versailles, that you guys are closer again to making, understanding, and maybe altering the ways how we see it. You're not going to do in this architecture university, you're not going to challenge all the regulations. But once maybe there's an idea, you started doing something, it gets to a next level, you start to do interdisciplinary collaborations with other universities. And then maybe slowly you can change things. It takes time, huh? But and it's true. That's also why we do these lectures, because you guys should be inspired by seeing other things, what is happening around you, and not get your head stuck in the sand and not see anything, because there is really a lot happening at the moment, and all over the world. If it's in China or in Germany, there's actually really, really a lot of things. And the whole process of building is going to be disrupted in a way, because of materials that are not there anymore, because of the Chinese having in all their factories, they buy 50% of all the robots worldwide. They took over KUKA, the robotic maker. So if you go to a regular factory floor now in China for making interior stuff and all this, half of the things are all robotic. So we're just behind at a certain point, and it's going to be interesting. Huh? I think you live in very exciting times. Look at your cell phone. We were born in an age where there was no cell phone, and my cell phone now is probably 1,000 times more faster than what my computer was in the 90s, and with more capacity on this little iPhone. Yeah. So I told you already, I bought the last one because you can do 3D scanning with it. So I think you guys live in fantastic times. So thank you very much, Oliver. Thank you, everybody.